Welcome back to Geology 315, Structural Geology. Today we're going to talk a little bit about field mapping and some of the things that go into what we call field mapping when we go out as geologists. And really, it doesn't matter if you're a structural geologist or what you're doing as a geologist in the field, note keeping and organization are the key components that you have to deal with when you're out in the field. And this is something you should get used to doing as you're going through your geology courses. We deal with outcrop descriptions. So as you go through your courses in igneous and metamorphic petrology and sedimentology, geomorphology, you want to be able to learn or keep in your mind how you describe the things you're seeing. We're going to talk a little bit about components of a geologic map. We're going to talk a little bit about geologic contacts in terms of primary contacts, depositional, unconformable, intrusive, secondary contacts, fault contacts, shear zones. We will hit structural contours a little bit later on in the semester, but these are going to become very important to our understanding of structures in the subsurface. So let's talk about field notes. Geologists typically have a field notebook, and their field notebook is oftentimes set up something like this. In this example, we're looking at a project in the Tucson Mountains. Of course, you put the area where you're located and the date that you're there. And you're going to record field stations. Your field stations are every place you stop to collect information. This is your data collection point. So here is an example where you have structures. These are looking at sedimentary rocks. If you've not had sedimentary geology yet, you may not be familiar with all of this. If you've had sedimentary geology, this should be familiar. But you're looking at bedding, cross bedding, ripple marks, parting lineations. And note over here that they've recorded strike and dip. Now they're using the quadrant method for strike and dip here. You could just as easily record this using the right-hand rule. And there's a description of what they're looking at. So in this first one, they have bedding. It has a strike and dip of north 29 degrees west, 65 degrees to the southwest. And it's a fine-grained sandstone. Next one, they come to another bedding plane, north 35 degrees west, 58 degrees southwest. This is a thin limestone interbed. Then they're defining some of the structures within those beds. There's cross bedding, ripple marks, and parting lineations. Ripple marks and parting lineations typically form lines or linear features. If you remember from the lecture, if you've not seen it yet, it will be in the lecture from TASA Earth. If you've watched that already, you'll understand that these are called linear features or lineations. And they have a plunge, which is an angle, an inclination, and a trend, which is a direction. And over here is the note of what kind of ripples, what kind of parting lineations, and so forth. You can go down through this and you can see all the different things that are labeled as well as drawings. So notes must correlate with map GPS locations. Today, we would be using GPS locations. So each one of these notes would also be someplace over here where your GPS location. You'd add that as a column to your notes. All measure structures must be recorded for later stereographic analysis. This just means looking at more detail. It could be air photos. It could be satellite images. Photos must be indexed by map station, which is what we have here. And rock mineral samples must be indexed by station ID. So if you collect rock mineral samples, and this is why we carry backpacks, or sometimes why we take graduate students in order to carry the rocks and minerals, you need to record where was the sample collected from, and a little bit of information about that sample. Notebooks also become a good place for sketches. You are correct. We now carry phones or phone cameras with us every place we go. So you can take pictures as well, but it's often nice to be able to draw in what you see. So practicing sketching within the notebook is always important. In this case, they've sketched in some formations, conglomerate, a sandstone, and they have a fault location. So it gives you an idea of what you saw when you were out in the field. Of course, you'd also want to take a picture of this. Some of the rock descriptions at your map station. What is the rock name? Is it igneous, sedimentary? Is it metamorphic? You want to know the color, mineralogy, texture, primary features, ripples, cross bedding, vesicles, etc. Growth characteristics. What's the weathering look like? Is it a ridge former? Is it a slope former? If you know the formation, you need to know the name, write down the name and the age. And you look at the types of contacts present in the outcrop. How are these formations coming together? Or igneous rocks coming together? When we look at a geologic map, much of this information you're collecting and putting in your notebook will then be transformed onto that geologic map, which includes description of structural symbols such as bedding, lineation. You're going to have a lithologic column. So this is going to tell you what is the rock types, what are the formation names. They're going to be in chronological order of the formations from young on top and oldest on the bottom. You're going to use the correct symbols. There's going to be different types of lines that show you what a fault is, whether it's a depositional or unconformable contacts. Of course, you're going to add a title, which includes your geographic location, your north arrow, both geographic and magnetic north. Typically, you'll also put in your magnetic declination, the scale, ratio and graphic, a border, which bounds your map with latitude and longitude areas, and of course, authorship and date of completion. This becomes very important so we can track when and who made the map. So if you look at a geologic map, you're going to find the same thing as what we've been learning in a topographic map. You're going to see that you're going to have longitude and latitude located along the edges. You also oftentimes will see the range and township information. Of course, your scales, north arrow. Over here is our explanation with our formations. And note that we have ages of those formations, oldest at the bottom, youngest at the top. Types of contacts that we see in the field. So this is going to be a contact type in the map. Types of faults. And of course, other linear features, strike and dip symbols, overturn symbols, foliation symbols, and so forth. You'll be learning more about these symbols as we go through the semester. Just wanted to show you a few examples of these things that I'm talking about. If you've been out in the field and you've seen these things, if you've paid attention to some of the images that your faculty have shown you, you've seen some of these things. This is a conformable contact. This is a nice red bed making a contact, and right now this probably is a sandstone, siltstone potential to sandstone contact. But looks like these beds are fairly horizontal, but we can see also up here there's another contact, a little bit more gradational, between some sort of a purplish bed into a greenish yellow bed. And of course, we go back into a red to tan bed up here. And you continue to follow those contacts. Those are conformable contacts. We can take strike and dip measurements along those contacts. And of course, we can collect samples and we can describe the rocks as we move our way up through the interval. Unconformities are also commonly found in the field. And you need to remind yourself about unconformities. There are disconformities, which is just a loss in time, an erosional event, oftentimes in horizontal beds. So here we have Jurassic sediments. On top is Miocene volcanic. So there's an age gap. We've lost some rock. And so that's a disconformity. Angular unconformities, where we have tilted beds and then erosional surface on top of the tilted beds. And then we put more horizontal beds on top. That's an angular unconformity. And of course, then we have this non-conformity, which is the erosional surface between igneous and metamorphic rocks and your sediments. When we go out in the field, we oftentimes map contacts. Contacts become very important because it helps describe for us what is happening out in the field. Plus, it allows us to place the contacts on a geologic map. I've just listed a variety of contacts here. There are intrusive contacts, which are shown here. These are vertical dikes, probably basaltic dikes. There are fault contacts, and these fault contacts oftentimes are filled with a lot of stuff. Cataclastic rocks produced by the grinding action in the fault. That's kind of what you're seeing here. Fault gouge is a fine powder, so it'd be the finer grains parts of this cataclastic type thing. Fault breccia, angular fragments that bound together by fine-grained pulverized material. Slicken sides, we'll talk a little bit more about slicken sides when we talk about faults, as well as mylonites. Drag folding, we'll hit on that as well. I can show you a picture over here of some drag folding already. Here is a contact between sedimentary rock layers. You can trace them across a fault. In this case, the hanging wall, which is this side, is dropping, so this is a normal fault. And you can see that This block has gone up, which is shown by the arrow, relative to this block, which has dropped down. And you can see that there's a fold that comes into the fault. That's a drag fold. And it's the result of movement along the fault itself. Well, again, we will talk more about that, but this is a really nice example of fault contacts, bedding, or other type of bedding contacts. And down here, this is a metamorphic rock, so there's actually potentially a disconformity contact, which is across where that metamorphic rock is exposed. When we did topographic maps, we learned something about the rule of V's related to contour lines. And I hope you all remember that. So if not, go back and look at the rule of V's for contour lines. Here we're talking about the rule of V's related to contacts. This is where the rocks are making contact with each other and where the contact crosses a valley or a stream valley. And the basic rule is, the rule of V states that as a bed crosses a valley, it will form a V with the sharp point of the V pointing in the direction of dip. The point, the end of the V points in the direction of dip. That's extremely important when we're looking at geologic maps. And it's also important when we're drawing geologic maps. We have to draw them incorrectly. The diagram on the right here shows you all the possibilities of beds dip upstream, V points upstream, blunter than contours. So you can relate the contour lines to the bed itself. So this would be the bed. These are the bed contacts. These are contour lines. Horizontal bed, V points upstream parallel to contours. Beds dip gently downstream, V points upstream sharper than contours. Beds dip with stream gradient. There is no V shaped. Again, if the beds are dipping with the stream gradient, you won't see the V. Beds dipping steeply downstream, V points downstream, direction of dip. Beds are vertical, no V shape. So if we see contacts running straight across the stream cut, we know that's a vertical bed. Again, this is a really easy way to identify igneous dikes and such. This is just a nice example here of the rule of V's in a block diagram. You're going to be working with block diagrams in lab. I'm going to go through a couple examples in just a few seconds here. But what we see here is this is the dipping unit. This is a cross-sectional view. This is a map view. When we're looking at a map view, we have a north arrow. So this is looking down, say, from a helicopter, or you've just climbed the biggest tree in your yard and you're looking down on the ground. This is the map view. This is a cross-sectional view. This is a cross-sectional view. This is kind of like the side of a layer cake when you cut open the cake before you get to stuff some of it into your mouth and go yummy, 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 yummy. Here is a dipping unit with a dip of 20 degrees. That's fairly shallow. You're going to have a fairly large V pointing in the direction of dip. As we get closer to 90 degrees, or a vertical bed, in this case 50 degrees, that V gets a little bit smaller. Once we hit a vertical bed, there's no V at all. So look at this diagram, embed it into your brain in some way, so you have an understanding of how beds will V in relationship to the dip direction, but also the dip angle. The other thing we have to know when we're dealing with geologic age, or geologic maps, I can talk, is knowing the geologic age. So if you do not know the geologic time scale, please go online. I think even in the App Store, there are places you can download apps that have the geologic time scale, and you can have it right on your phone. So you can always look it up. You should start getting used to looking at these symbols representing the age. PC for Precambrian, C for Cambrian, O for Ordovician, S Silurian, so forth. Tell the difference between a Pennsylvanian symbol and a Permian symbol, between a Triassic symbol and a tertiary symbol, because sometimes the only information is you have is the age of the formations themselves. And from that, you can imply structure as well as direction of dip of units. So the key here is understanding the difference between a geologic map, which is a surface, and the cross-section view. And this is a fairly simple block diagram, which shows horizontal beds. If you remember your law of horizontality, you should remember that beds are laid down in horizontal layers. And so the oldest is at the bottom and the youngest is at the top. Give me a second while I get my pen. So this is 1, 2, 3, and 4. 4 being our youngest unit and 1 being our oldest unit. Of course, if we're looking at both sides of this cross section, we have to label this side as well. 1, 2, 3, 4. And since this is a map view and we want to have some data that tells us what's happening to the rocks in the subsurface here, we have to put in a symbol. So a symbol for a horizontal bed is a circle with a plus sign. Now I've mapped this. Let's put our north arrow on here so we have a good feel for north. And that's a map view. So now we've mapped this. We've done both a map view and we've done a cross-sectional view. And that's basically what you're doing when you're working on block diagrams. Give me a second while I erase this. Forgive me, I've lost my mouse for the moment. So when we're looking at our block diagrams, there's a variety of things you need to know. Of course, you're going to want to map the surface. So you need to add strike and dip symbols. You need to look at the dip of the unit. You have to V your contacts. You have to draw in the contacts in the correct direction. Contacts are always going to be parallel to the strike. You have to dip your units in the correct direction. That's going to be in the direction in which our dip, our smaller part of our strike dip symbol is pointing. And you have to have the correct angle. In this case, you read off of there 75 degrees. That angle right here is 75 degrees. If you know the ages, you can put in the ages as well. So this is Precambrian, Cambrian, Ordovician, Silurian, Devonian. And of course, you have to put those ages in on your map view. And note that over here on this side, this is all Devonian because of the steep dip. Note also that this is oldest, this is youngest. So you should be able to turn this all horizontally and get an idea of what it looks like. Another example here, it's a shallower dip of 35 degrees. We're going Precambrian, Cambrian, Ordovician, Silurian, Devonian. So on this side view, we are able to get in some Devonian beds, Silurian beds, and Ordovician beds. But note, on our map view, the Precambrian is not showing. So I'm making an interpretation in the subsurface that the Precambrian is older than, therefore, is below the Cambrian. If I wanted to prove that, I would have to drill a well. And I drill down to that depth and say, okay, here's the Precambrian rocks. Example down here are some vertical units. Cambrian, Ordovician, Silurian, Devonian. Vertical strike dip symbol. Note that there's no V when you cross the stream valley. This is a little bit different, and these beds are overturned. Overturned beds are a little bit tricky to visualize the first time, but basically what you're looking at is horizontal beds that were one time had Precambrian on the bottom, but now has Precambrian on the top. So it's upside down. So this symbol shows us the dip direction, but indicates that the beds are upside down. And again, you can follow the contact lines, our V's, a little bit bigger than what we've seen before because this is a shallower angle, and then the continuation of the beds over here. Now I can show you just briefly here. Let me get my pen back. We'll just come over to the side here. If I have some horizontal beds and I compress it, and we're going to learn about this when we're doing folds, but I can compress this, and what will happen is I can do a gentle fold like that, or I can continue to compress this, and what happens is the fold starts to fall over. So these beds here are now upside down. Whereas the right side up here, they've been flopped over on top of each other and they're upside down. They're going later on in the semester, we're going to be investigating this and learning how to identify when a bed is upside down. So let's take a look at one of our formations where the beds get younger in the direction of dip. Here's a map view. We have a strike and dip symbol. We don't know what the angle is. We know that the beds, the contacts, all are going to be striking parallel to that strike symbol, and the dips have to be going off to the left. If the dips are going off to the left, then this bed is oldest, and we get younger in this direction. Here's a bed that's dipping to the east, but we don't have the map view. So in this situation, we'd have to draw in the map view. And forgive my not straight lines, but I'm going to do the best I can. So these will run parallel to strike. And we can add additional strike and dip symbols. Note, we also have to finish this wall. Again, we try to keep that as straight as we can. Forgive my crooked lines. And then, of course, you can number this. Again, this has to be the oldest. 2, 3, 4, 5, 6. And we would number over here too. The ones that are showing are 3, 4, 5, and 6. So I'm hoping you're seeing this, is if we have a set of horizontal beds, numbered 1, 2, 3, 4. And if I compress this, I can result in the beds being tilted. I can then erode off part of these beds. And what I'm seeing then in the field is resulting in what we see over here. So again, we can number them 1, remember that's the bottom, 2, 3, 4, 5. I'm hoping this is making some sense, because what we're talking about is deformation. We're talking about the tilting of originally horizontal layers. And we just need to start learning the age relationships between the layers and the relationship with the strike and dip symbols, because the geologic map is going to give you the information so you can build these cross sections. This is a slightly more complicated diagram, but we can go ahead and put in some cross-sectional views. This one has the map view. Map view's done. We know that we're striking north and dipping on in this case to the west. And over here, we're striking still north, but dipping to the east. So this structure is going to be a little bit different. And so what we need to do is we need to start looking at it in terms of what kind of structure would have that kind of an appearance. And forgive my lines. I'm just going to put these in fairly quickly. And the ones that make contact over here would come across there. Of course, again, we'd have to label these. And you'd have to decide what is the youngest and what is the oldest if we were looking at this. In this case, we're looking at an anticline. So the oldest is here in the center, and we get younger in the direction of dip. Again, we'll learn more about folds later on in the semester, but this is sort of a review. You should have seen some of this. If you took My Geology 105, you have done some of this already. When we're talking strike and dip, what you've been learning, especially when you watch the other video on the TASA Earth, is you're going to learn a little bit about strike and dip, and that the dip angle when we're measuring in the field is at 90 degrees to strike. It's always at 90 degrees to strike. But when you're out in the field, nature doesn't cooperate. And so sometimes the exposure is not cut perpendicular to the strike. And the angle you might end up be measuring is called an apparent dip. We're going to learn more about apparent dips later in the semester, but this angle, the apparent dip, is always going to be less than the true dip. So the true dip on this formation, these sets of formations, is going to be always greater than 35 degrees. So this is not the true dip that's being mapped into this cross section. This is an apparent dip. And so again, we're going to be dealing with that a little bit later on in the semester. Another more complex anticline-syncline pair. I'll go ahead and stare at it for a while. It's a little bit more complicated than what we've already gone through. Unconformable contacts, notice they're put in a squiggly line in the cross section. It's denoted by a hasher mark in a map view. And of course, in the explanation of a map, you'd have this as denoting your unconformity. Domes and basins, in this case, we're looking at a basin because we're dipping in toward the center, and it's youngest in the center. Mississippian, Devonian, Silurian, Ordovician. We're getting older as we're moving away from the center. So again, when we're looking at structures, you can start mapping these things by mapping contacts, and then suddenly you start to put together what the geology is of an area. Another fairly complex anticline-syncline pairing. Just again for review, this symbol that you're seeing here denotes a plunging anticline. A plunging anticline forms what's called a nose, and it plunges in the direction of the nose. Note the symbol for a plunging anticline. That, and it's this outward arrows with an arrow pointing in the direction of the nose. This is a plunging syncline. It looks exactly the same in map view as the anticline, except for we have to look at the age relationships. The syncline is younger in the middle, and the beds are dipping toward the center. And we have a symbol here which shows the symbol for a syncline. Once we put the arrow on it, it's a plunging syncline, and it plunges away from the nose. Down here is the nose. We're plunging away from the nose in a plunging syncline. You need to get those things into your head if you don't have them there already. Again, a more complex block diagram with overturned synclines. This is a symbol for an overturned syncline. This is a symbol for an overturned anticline. You see the strike and dip symbols with overturned symbols where the beds that are mapped in the field are overturned. Other strike and dip symbols show the beds that are not overturned. Again, I'm asking you to note the age relationships because that becomes important whenever we're talking geologic maps or cross sections. Fault classification and block diagrams, we have to think a little bit in terms of faults and what they do. Later in the semester, we'll spend more time on faults. I'm kind of coming back to the idea that you've seen these in 105 or also in a physical geology course. If not, I'll ask you to go ahead and look. You can Google these. You can ask questions about them. But this is a left lateral strike slip fault. Left lateral just means if you're standing on this side of the fault, facing the fault plane, the other side is moving away from you to the left. And again, if you turn on the other side, looking across this way, this side is going off to your left. In a map view, we use these types of symbols. It just gives the relative motion. In a cross-sectional view, the minus is the wall going away from you. The plus is the wall coming towards you. This is a reverse dip slip fault. Sorry. It's a reverse dip slip fault. And so this is a vertical fault. In this case, this is the hanging wall. It's going up relative to the footwall. And we denote it with the up and down arrows, as you see here. We denote, because this is a vertical fault at a fairly high angle, we use up and down symbols, U and D, to denote which side of the wall went down and which side of the wall went up. This is an oblique normal dip slip fault and a right lateral strike slip fault, which means we have both strike slip motion as well as vertical motion. So here we have the strike slip symbols and the minus and the pluses denoting the strike slip motion. And we have the arrows. In this case, the footwall has gone up and the hanging wall has come down. And this is representative of a normal fault. So that's a little bit about how we map and how we work in the field as geologists. Again, you'll note the notebooks, the backpacks, and of course, the lovely, 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 lovely geology. And yes, I wish we were out there today. Hopefully at some point we'll be able to get you out in the field and you'll be able to practice some of these things on your own. What I want you to do again is if you watch this video, watch it again, take a look at the lab. I'll probably put together a little bit of a video that goes through the lab as well. But take a look at the lab and start putting together your idea how to deal with block diagrams, how to measure your strike and dip symbols, and how to use strike and dip in both the quadrant and the right-hand rule methods. That's basically what we're going to be concentrating on today. Again, I thank you for your time and stay well.